be on the midterm, those of you on the WebEx who are wondering what just happened. Oh, that's kind of interesting. Why is it doing that? Let's find out. I want to find out what's going on with my screen sharing. Hold on a second, guys. I'm trying to figure out how to change the screen. I can't mute you guys today, so you will need to mute yourself. If you don't mind, please. You have to take a peek at your connection and mute yourselves for me, pretty please. Okay. This one. See if this is it. If someone's making tons of noise out there, just take a glance and see if you're muted, please. Or you can just mute your microphone on your cell phone. Yeah. Anybody recognize who that is? All right. Okay. Let me try this again. I'm trying to get this to duplicate my screens. Okay, that's what I want right there with that option. Yep. Bingo. Okay, great. This is the 5:30 Monday session. We'll welcome everybody to this. Okay, that should get us where we need to go. All right, good afternoon, everybody. Welcome. Is there anybody in here who's on WebEx? No? Okay, if somebody does get on WebEx and you can actually see me on the screen, will you do this for me? And if you can't, just do... Are you on WebEx? No, okay. You're just giving me the thumbs up anyway? Okay. Sure you do. Okay, thanks. All right, so today we're going to go over the homework that was assigned as promised. So we've got a few things to kind of review. This will be partly review as well. So for this first problem, we can sort of back up a little bit, but let's take a stab at this thing. So I've got two locations in memory, and what I'm doing is loading something into a register and then writing it back out to a different address. And so when I load it in, I'm only going to load a byte. So this raises a few interesting questions. If I only load a byte of something into a register, what's going to happen to the rest of the space in that register? Is it going to get zeroed out? Is it going to be left alone? Maybe there's something there already. Is it going to be sign extended? What do you think will happen? So that's one thing we've got to figure out. And then when we go to store it in another location, is it going to store the whole register and overwrite what's there? Or is it going to remember that only one byte was brought in, and so it's only going to overwrite that one byte? And to make matters worse, we are also referring to big endian and little endian changes here. So do you guys remember what that means? Big endian, big end and little end. So there's a link in here that kind of takes you to this page. You'd have to read through it a little bit. Just remember that what's at the top of the page is a solution for the prior page's problem. And then you have the problem for big endian, little endian, the answers on the next page. So that's kind of the way they organize this website. So the top part of the screen has nothing to do with the problem down here. They just make you think, and then you go to the next page to get the answer. So big endian would take a number like 1, 2, 3, 4, 5, 6, 7, 8, which you see down here in hex. And if I zoom this up a little bit, I don't know if I can really make it bigger. Yeah, that's not bad. So here they're showing us the number they're trying to put into this register, 1, 2, 3, 4, 5, 6, 7, 8. And they're asking us, where's it going to be? If it's Big Indian, 1 and 2 will be at address 400,000. 3 and 4 will be at 400,001. 5 and 6 will be 400,002, and so forth. So with Big Indian, the lowest address gets the highest bits. The big stuff goes first. The big guy goes in first. Okay, please check your microphone and mute yourself if you're not muted. I can't mute you from this platform that I'm using today. So just take a peek at your cell phone, and you can just mute it on the cell phone. You don't have to even mute it in WebEx. I appreciate it. Thanks. Okay, so register T1 contains this address, and register T2 contains another address. Here are these two addresses in memory. Here's what's in those locations. So lots of things to figure out here. If I'm going to load byte unsigned from 0 T1 into T0, what am I loading? Am I loading this number? Am I loading this number? Well, what am I doing, first of all? Do you guys have an intuition? Am I trying to put the address into T0, or am I trying to put the contents of the address into T0? So it sounds like several of you think contents. Does that sound right? All right, so if it's contents, then we're targeting 33, 11, 44, 22. So if I'm only going to load one byte, which byte is it I'm going to load? On the right. The least significant byte? Yeah, so if I don't have a way of telling it which byte, that to me seems like the safest bet. You could make an argument to the other way around. Why are you giving me all the bits like that could be insignificant to the right of the decimal point? Why aren't you giving, this number is in the millions. I'm a banker. That's what I want to know, not how many cents. So why aren't you giving me the biggest list? You could argue the other way, but in the absence of something else, that's the way they designed it, is to take the least significant byte. So 22, I think it is. We're going to be pulling 22 in. And now that I have 22 in T0, I'm going to store it in T2. And so the question is, what's in T0 now? Is it, the whole thing that was in there before? Is it just 22? Is it 22 4 times in a row? Is it zeros and then 22? How would you design it? I'm not even asking you how this actually works. I'm just asking you for your gut instinct. If I told you to load just that byte, load byte unsigned, and we decide it's 22, and the register's got room for 32 bits and you're only dealing with 8, what would you do with the other 24? Zeros? Does that make sense? You guys agree? Let's see that. Let's try that. So that's decent intuition. Now, do you know absolutely for a matter of fact that that's exactly what this thing does? No, but that was your instinct? Trust it. Trust it. You've been exposed to enough stuff, even in this class, that you may not even appreciate that you've developed some intuition. If you get stuck, trust your gut. All right, you're going to be right more often than not. All right, so let's say it's 00000022, and now you're going to store that word in, where are we going to store it? T2, right? Which is this address. So we're going to be storing it here. So the question is it going to get stored as 22000000, or is it going to get stored as 00000022? And is this Big Indian or Little Indian? Did I even tell you? Yeah, I did. Big Indian addressing. So I tell you Big Indian. So if it's Big Indian, what's the rule for Big Indian?
The larger number was part of the memory. So I think 22000.
So big one goes where? So if 22 is the least significant number or the most significant number here? Oh, we have debate. 00000022, 32 bits. What's closer to bit 0? Or is the 22 at the 0 end or the 31 end? It's the 0 end. It's at the 0 end. So it's the least significant bits. 2 times, or whatever the value is, times 2 to the 0, 2 to the 1, 2 to the 3, 2 to the 4. Remember the positional numbering system that we looked at? Okay, so let's go back over to this side again. And let's see what we find here. Big Indian means it's 0, 0, 0, 0, 0, 0, 2, 2. That would be the 7, 8 in this equation, correct? And where did the 7, 8 end up going? In the high ordered address. See the addresses here? 400,000, 400,001, 400,002, 400,003. This is not at the 0 byte. It's 4 bytes past it. So if you're going to put 7, 8 at the top, and you're going to put 1, 2 at the bottom. So what I would do if I were you guys is, what this is telling me is that the 22 goes first. And then 22 will be at address 4, then 0s at 3, 2, and 1. That's what Big Indian here is telling me. But it was also Big Indian when I pulled it in. So I would find a simulator, poke around, use, you guys have a chat group going, right? Hash it out. See what you get. There is one right answer to it, but I want you guys, this is what, worth a few points. It's inconsequential to your grade, but I want you guys to kind of hash it out a little bit on what you think. Not all of you are going to give a crap about it. I get that, right? We all have lives and stuff like that, but some of you will. This will bug you, and just get a little chat going on it. See if you guys can argue it out, because there's like 3 other sections that are going to be trying to figure this thing out at the same time. And you can go and look on those websites that have copies of people's turned in homework solutions and things, and you can probably map it out. I've changed the numbers, but the pattern, of course, is going to be the same. Big Indian, Little Indian always do the same thing. They're always going to take the low one and put it in the high one or the low one. So I didn't exactly throw you the bone on that one, I realize. So it's part of my trick. But I did have your undivided attention for that, didn't I? See? So it's a trick. All right, shall we move on to the next one? So what somebody think? What would your gut tell you on that last one before we just wrap things up there? How would you finish that up? Yep, all 0s and 22. So my advice would be trust your gut, and then see if you can figure out if it's right. And if you can't, stick with your gut. Right? Try that. Nope, you don't have to justify it. Just you put the answer in. Okay, here's a large constant into a register. It's 32 bits long. All addresses have to be 32 bits, right? No exceptions ever. They always have to be 32 bits. If you're going to go knocking on Ram's door, you better have the full room number. You know, don't just go knocking on room number 8 on every floor until you find it. Know which floor you're going to. Have the full address. If you're gonna, it gets worse than this, right? So I remember she was in room 8. That's all I remember. I'm just going to go knock on all of them. So you've got 32 bits. You're going to have to put a whole 32-bit address together before you can go to memory. And we only have 3 types of instruction formats that we've looked at so far. What are they? R, I, talk like a parrot, day, I, and J, right? And they have 32 bits in each of them, but they have different characteristics. Which ones can pull in a constant? That you can include a constant right in the instruction itself and get it into the computer. I. What else? Is that the only one? J. Okay, and just those 2?
R.
Why R?
For example, at immediate, we can have it constant.
Yep, so you remember the shift amount field in R? She's right. All 3 of them have space for a constant. We rarely use the shift amount one as we're talking about here exactly. But they all 3 have space for a small number. How big is the space for an immediate in an R-type instruction? Nope, much smaller. 5 bits. 5 bits. What about in an I-type instruction? How many bits can we use to put a constant in? 16. And then what about in a J-type instruction? 28. Se cambio la resolución. Why does it change my resolution? 26. So 26 because the remaining 6 are the opcode, right? So this is a problem because none of those are 32. And we always need 32. So if you're the compiler and somebody hands you a line of C code, and right there they give you a constant, maybe they're not going to give it to you as binary. Maybe they'll give it to you as a big decimal number. Maybe they'll give it to you as hex. If it's too big to fit in any of those 3 instructions, if it's a 32-bit number, what are you going to do? How are you going to get that number into the computer? So that's a problem that we have to figure out how to solve. And what we saw last week, or yeah, it was last week, today's Monday. What we saw last week was a pair of instructions that would allow us to at least chop that big 32-bit thing in half that C programmer gave us and pull it in pieces. Now, if we want to use an I-type instruction, cutting it in half is perfect because half of it is 16 bits. That's how much space we have. We can chop the thing in half. So what that approach would argue doing is you start off with the 0, 1, 1 here that you see, and you continue on for 16 bits and stop here and just figure out what that number is and pull it in. Now, I could change this to decimal to make it a little easier for me to understand what it is, but it's still a pretty big number. It's 16,000 and something. And so I would pull that in an add I. How many bits do I need for a number that big? I need 16 bits, and that's exactly what I've got. So we learned how to split a number like this in half and pull it in 2 pieces. Do you remember what the commands were? Exactly the 2 MIPS commands that we used in order to make that happen. It was in section 2.10.
LUI and OI.
So remember LUI? Does that ring a bell? Load upper immediate. So what that's going to do with an I-type instruction is take the constant that you gave it. It's going to assume it's 16 bits because that's the way I-type instructions work. It's going to pull it in, but it's going to load it into the upper half of a register. So it will slide it over and drop it in at the top. Mission accomplished. So we've just got the 16 bits there. The problem with just continuing on, there's lots of ways that you can get the lower 16 bits into a register. Why can't we use most of them here? Why do we use ORI and OR our way? Why not use add or any of a number of other math type commands to get it in there? Yeah, so do you guys know what sign extension is? So sign extension is one where you drop a number into a register. It's not big enough to fill it out. The computer says, oh, well, you gave me a number that doesn't need 32 bits. Like you told me to put the number 3 in a register. Okay, I can do that. I'll put the number 3 in there, but I'm going to go ahead and take the sign of this number and duplicate it through all the remaining bits all the way up through the bit 31 to the very end. And it's called sign extension, just to make sure we're all on the same table. So if the leading bit is a 0, that gets duplicated. If the leading bit is a 1, then that's what gets duplicated. So if I had you write as a 2's complement number, the number 3, how would you write it? Well, first of all, what's 3 in binary? 1, 1. Is that also the way to represent 3 in 2's complement? What does this look like when you see this number in 2's complement? Looks negative to me. Does it look negative to you? So what do we need to do to make sure we interpret this correctly as a positive number? Add a 0 to the front. If I tried to represent the number 3 in 2's complement in a field that was only 2 bits wide, this would be overflow. It's impossible to do it. So I must have at least 3 bits to represent the number 3 because the leading bit needs to be 0. So is there any harm in tacking on more zeros? Let's say you take this now and you drop it into a 32-bit register This is only 3, so I have 29 left. Is there any harm in taking this one and duplicating it over 29 more times? No. What if the number is -1? Does anybody remember what -1 is in 2's complement? All 1. So let's say this is 1, 1. And I'm going to need a third bit here as well, but I don't really because this also is -1. But let's just make it 3. So now my question is there any harm in taking this leading 1 and copying it over 29 times? Does that change the value of my number? In 2's complement, it doesn't. That's exactly why we use it. In 2's complement, if you got enough bits to represent significance where the leading 1 is enough to help you sort out if we're dealing with the top half or the bottom half of the numbers, you can duplicate that leading bit as many times as you want and never change the value. So this is a -1 in 2's complement, a single 1, so is a pair of 1, so is 10 ones. It's all the same number. Just like a single 0 means 0, so does 2 zeros, so does 10 zeros. Doesn't make any difference. So the reason why I can't use one of these commands like add to get the bottom 16 bits of this number coming back to the problem is if you drop the bottom 16 bits in, this little guy is going to just start copying and he's going to erase everything you just put in there before. He's going to sign extend. This is called sign extension. He'll sign extend it all the way out to bit 31. And there goes the first 16 bits that you've got. Yeah.
So how does a computer understand and recognize 2's complement and knows what that binary number is, and then how does it ignore the other bits?
So that's like one of the most important things that you need to get out of this class. So the question is, how does the computer know whether this is supposed to be a 2's complement number, and therefore if it's one of these strings where it's supposed to like do this sign extension thing versus it's a register full of a bunch of status bits, in which case it's supposed to treat them individually, versus something that's supposed to be ASCII text, so I'm supposed to take 4 bits at a time and treat them as alphanumeric characters, or a signed number, or 2's complement, or floating point, or something else. So how does it know? How does it know? If I showed you a string of bits, can you tell by looking at them how to interpret them? Oh, your answer better be like gut, no, right? So no, you can't ever tell. I have to tell you more. If I tell you, here's 32 bits and I found it in the text block in memory, you'd go, oh, it's an instruction. I know what to do with that because only instructions go in the text block. I'm going to look at the first 6 bits and figure out the opcode, and then I'm going to figure out which instruction type it is and divide the rest up, and then we're off to the races. If I tell you it's 32 bits and it's on the stack, how do you interpret it? What type of, so what did you just do? You just went like that. Why? Trust your instinct. That's correct. That's exactly the right answer. Why did you do that? You didn't even trust yourself, did you? But you had the right answer. That was exactly the correct answer. That's what I'm telling you. You guys know more of this stuff than you realize. So it's not enough information. You can't know if it's on the, you can put anything on the stack. You can put numbers and text and bits. So how then, so back to this question, when I do have my hands on a register with bits in it, how do I know how to interpret it? How do I tell the computer how I want it to interpret the contents of a location in memory, like a register? So let me ask you this. If I told you I wanted you to print it out as binary coded decimal versus add it versus and it, is that a hint as to what you should expect the contents to be?
Based on the instruction.
Totally based on the instruction. The instruction dictates exactly the valid range and interpretation of all the bits that you can point to or that are included. The instruction, if you need 2 different versions of add, one of them that treats the register as an unsigned integer and another version of add that treats the contents of the register as a signed integer, then have two different instructions. One of them called add u for unsigned and the other one called just add. Make sense? So the instruction is the only way you tell the system how to do it. The opcode is king, right? So that's the only way you know how to interpret stuff. So the two instructions are LUI and ORI. They're going to OR the two things in, and you'll end up with exactly the right combination at the end. And that's right out of section 2.10. Okay, let's move on to the next one here. The program counter is set to address 0 for the next instruction. So I don't know where we are right now, but the next instruction that we're getting ready to execute is in address all zeros. In that location, we find an instruction. It's 32-bit machine language representation of the jump command, which is opcode 2. There's several jumps, so I gave you the opcode, so you wouldn't be confused. So you could go look it up if you need to. If you maximize this command to jump as far away as possible, what will that destination address be? Well, first of all, how many bits can I pull in with the jump command? 26. So the jump command is formatted as a J-type instruction. It has 6 bits of opcode, and the remaining 26 are for an address. How many bits do I need to go to RAM to tell it what address to what location I'm looking at? Always 32. No exceptions. Always 32. It's like showing up with only part of the apartment number or the hotel room number. So 32 bits, and I only have 26. Where are the other 6 going to come from? Well, this is a designer's problem. And what we decided to do in many systems like MIPS was to limit people's ability to jump just anywhere in RAM with this command. And so there's some restrictions. It only has 26 bits. It's really easy to feed the address in, provided it's not too far away. So we're going to just take, for our first 6 bits, the 6 bits where this instruction lives, which is 0, 0, 0, 0, 0, 0, 0, 0, etc. So what are the most significant 6 bits of that? Zeros. So the first 6 bits of our destination will be zeros. And the rest of them, what's the maximum number we can put in 26 bits? All ones to 26 minus 1. Right? All ones. So it's 6 zeros and 26 ones. So what's that look like in hex? Well, it's almost easy. The ones part is easy. What's all ones in hex? Just a bunch of F's, right? But the first 6 are zeros, right? So how many binary bits per hex digit? 4. 4. So if there's 6, then the first 4 are 0, but the next 4 start off as 0, 0, and then the rest were ones, right? Because from here on out, it's all ones. So what's this? 3. 0, 3, F, 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 F. Should be what you come up with. Make sense?
So the opcode. So the first 6 bits are supposed to be the opcode. The opcode is 2.
The first 6 bits aren't from the opcode. The first 6 bits are from the address where this instruction was run. So in address 0 in memory, I go and look in RAM at address 0, and I find a 32-bit word. It's actually in 4 consecutive bytes, of course. And what do I find in here? I find 32 bits that are the jump command, and its only argument is all ones. So how do I format that? The first 6/8 of the byte, almost the first byte. Let me screw this up. Let me do it again. See if I can draw this a little better. So there's 4 bytes, right? The first byte is going to be 6 bits of opcode, and then we start the 26 bits of the one and only argument. So what's the opcode for jump? What is it?
All zeros.
Is it?
No, 2.
I tell you right here what it is.
0, 0, 1.
It's opcode. What does it say in the problem? 2. 0, 0, 0, 0, 1, 0. That's the opcode. Now you know it's a jump command. J-type instruction. You look that up on your reference card. J-type instructions have 6 bits for opcode and 26 bits for an address, right? So what are we going to set those remaining 26 bits to? Ones. So I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is a 0, and this is, something else. But that's not how we build the address. That's how we built the instruction. The rules for the jump command are just take the 26 bits that you've got from here and go back over here and get the first 6 bits from this. Add those two things together, and that's how you end up with a 0, 3, Fs.
No, we're building an address.
You're building an address. You're building an address in the same neighborhood as where the command was run. Make sense? Yep. So what do I do if I need to jump outside of this neighborhood? What if I really do need to jump someplace completely different in memory? I need a different instruction for that. This instruction will not do that. It will not accomplish that for me. So if I need to do that, then maybe I can use the jump register command instead. Do you remember where we saw jump register commands? So let me tell you what it is, and then maybe you'll remember. The jump register command points you at a register. So it has a different opcode, and its opcode is 0, its function is 8. Well, so it's an R-type instruction. So right there I know I'm not feeding 26 bits of anything into it. So opcode is 0, function of 8, and it takes a single, there's space to put 3 registers and a shift amount in there, but we ignore everything but one of the register spots. And we give it a register number. And we'll usually see a command that says jump return, or jump register rather, and the register they'll usually point to is the RA register. Anybody remember what RA stands for? Return address. So where are you going to usually see a jump to the return address in code? At the ends of procedures or at the ends of function calls, right? Exactly, guys. So I see people putting things in chat, which is yay. Let me pull it up here and make sure I can see. Yep. All right. Let me get back over. Thank you guys for doing that. All right. So jump register is cool because now I can tell you, I want you to jump someplace, but I don't want you to do this crazy ass thing of like putting an instruction together with these. Instead, I want you to go to this register. It's a full 32-bit register. I can put a full 32-bit address in there. It can be anywhere in memory that I want. Right, so what's the drawback of this? This makes my program run a little slower. How? It won't have to search through them. It can get to them fast, but you're on the right track, though. Who put the value into the register? God? You did in the line before. So you have to write one line of code to put the number in the register, and then you have to write a line of code to go and look at it and jump there. So it adds lines of code. It'd be better if you were jumping someplace close. I'd probably just want to use the jump command because I can do all that in one line. I can get all that done. So it makes your code a little longer, but this is foolproof. And there's no confusion ever. If you don't want to mess with this stuff and you're willing to write 2 lines of code, jump to a register. You can use T0 or T1, wherever you want. Just put the value you want there, exactly the one you want, and then jump to it. Works great. Okay, let's see here. If you use the jump register command, what's the highest address you can jump to now? All ones. Not 6 zeros followed by 26 ones. No. All 32 ones. F. So the answer is in hex, right? So it's all F's in this case. Okay, if you use a single add I command to place a destination address in a register, so let's write an add I command here. put something, what register do you like?
S0.
Okay, we're going to put an S0, and we're going to put a constant, so it's add I, so I'm going to have another register here, and then you have your constant over here. And you're going to use that to build an address into S0. And I'm going to restrict this to being of no value. So I'm going to ask you guys just to consider using 0 here. So what's the highest value I'm not even sure if I have room for the second one in there in that command. I'm getting cold feet on that. What's the biggest value I can put here? So tell me what's going through your head.
The layout of the I.
Okay, layout, good. I hear somebody say all ones. So this is an addition command, so what else are you worried about over here? How are you going to interpret it? Like back to the question, is it 2's complement? Is it... So does anybody know how this will be interpreted? If it's an add immediate? It's 16 bits, right? So what's the range of values? Do we want our computer to be able to add positive and negative numbers? Yeah, so why don't we divide this up? Half positive, half negative, sound fair? So if this is 16 bits, if I have 2 to the 16 combinations, how many of those should be positive and how many should be negative? 2 to the what? 2 to the, what's half of the number of that's in 2 to the 16th?
15 for negative.
2 to the 15th. That's half. Don't get caught by that. So 2 to the 15th for positive and 2 to the 15th for negative. So what happened to 0? Where am I going to put 0? I need that in there too. It's neither positive nor negative, correct? So we're going to have a 0 in here. Which side do you want to take it out of? The positive side or the negative side? So you really can only then go to 2 to the 15th minus 1, right? And on the negative side, you can go to minus 2 to the 15th. That's the way it works. So how am I going to encode these values in 16 bits? What numbering scheme should I use to communicate to the user which one of this range I'm talking about? When you sign magnitude or 1's complement or 2's complement or 2's, I hear a piece, 2's complement, correct, right? 2's complement. So in that case, this is an address. So what's the biggest number that I can put in here then? A 0 and all 1's, right? Is that right? So what's going to happen in the 32-bit register when I pull this in and drop it in? Yeah, and it's going to get sign extended because it's a math command and it's 2's complement. So this thing's going to get pulled into the system. It's going to get dropped into a 32-bit register. You're going to have your 15 1's and then a 0, and the 0 will be copied over for the rest. Right? It's not a very big address, is it? So if I feed this register, now that I've built these bits, if I feed it to a different command, one that expects this to be interpreted as not a 2's complement number, but instead as an address, are addresses positive and negative like 2's complement numbers are? No, they're only positive, right? So if I build it one way and interpret it with something else, anybody, are the programming police going to come and arrest me? Like if I tell you, I want you to build this thing bit by using bitwise insertion, and you do the whole thing, and you just like torture yourself with 100 lines of code, but you get the address that you want, and then I hand this thing, people are trying to figure out, like, what's he doing? What is this? Are these flags? Is it a counter he's building? What's going on? And I finish the whole thing, and I hand it to a store word command, and store word says, oh, it's an address. And people are like, oh, an address? You went through all that to build an address? Why? So if I give you this, what's the maximum address that I can specify in 32 bits? Forget about add I. What's the biggest address in my system? It's all ones. So let me ask you this. Is there any way to use the add I command to get this number? It all hinges on this bit right here, doesn't it? What's going to happen to the value in this bit? It's the 16th bit. It's this bit here. It's the most significant one I can pull in with add I. What happened to the 0 when I put a 0 in here? So what's going to happen if it's a 1 instead? Same thing. So can you make this all ones, at least the 16 bits? What is that value? In decimal, what is it? What is 16 ones in 2's complement math? -1. Right? It's just a -1. It's all ones, the closest you can get to 0 in 2's complement. So that's a -1. So is that. 2 ones. So is this. Those are all -1. You can add ones to the beginning or zeros to the beginning. It never changes the value in 2's complement, right? So just put a -1 in decimal or FFFF in hex. And the system, because it's an add I command, the system believes you're dealing with math. And its rule for 2's complement math is to sign extend the most significant bit. It doesn't know you're planning on using this as an address. That's your business. But because it's a math command, it will sign extend this out all the way, and you will end up with 32 ones. You hand that to a system and as an address, like store word, and it'll go to the last location in memory. Presto. Neat trick, huh? Yep.
So, is it 16 bits? Is that only 4 numbers for hex?
Yep. Yep. Only 4 numbers for hex because it's 16 bits. Exactly. Okay. Tricky, huh? But the reason for this one is not to trip you up, but it's to get to the question he was asking really earlier, which is, who cares if you think it's a math operand here, but then you end up using it as an address later? No one cares. It's just bits to the system. They don't care. Okay, you load a branch command from an instruction memory, and as you begin to process it, you notice that it is asking that if T1 equals 0, that you're supposed to jump to an instruction that's 4 instructions further down the page. Okay, let's go back to the laundromat. This is freaking me out that it sticks. I have no idea. It's a very weird sort of feeling. It feels like it's wet or something. I don't like that eraser. It's like picking up a leech or something. I can't quite put my finger on it. Okay, so T1 equals 0. So anybody want to take a guess at what the command looks like? Doesn't have to be right. I'm not asking you to tell me what it is. I'm asking you to guess what it is. Yeah, so what's the line of code I'm going to write to see if T1 is equal to 0 and then jump to something that's 4 instructions down? Let's just start with that. What would that line of code be? You're going to use add or subtract? I mean, how are you going to test to see if T1 equals 0 and then if it is branch? How about a branch command? What branch commands do we know about? We know about BEQ. What else? Have we learned any others? B and E? Yeah. What does this one stand for? Branch if not equal. Branch. And so we talked about how we have to do things opposite because usually programmers put stuff at the top, and that we're not going to confuse that right now. This is just, I've already given it to you as assembly. So this is going to be the branch equal one. And what are we feeding it as arguments? First of all, is it an R, I, or J type command? Is it? You can. Where would you find the answer if you needed to know? The MIPS reference card, right? So if I don't give it to you in the study guide on Wednesday, make sure you have it by your side at the exam. Print it and bring it. But God forbid, but it can happen, I can forget it, but my plan is to include it as a pair of pages in the study guide. You can bring and should bring the study guide as well to the exam, as well as a single 8.5 by 11 inch sheet of double-sided paper with machine created or human written notes. So it's a lot of rope. It's a lot of rope. If you end up printing the entire book with a magnifying glass, you will spend your time trying to read the book. Now is the time to read the book, not during the exam. You won't have time to do it. Okay, so branch equal, what should my first argument be? Where it's going to go, which is T0. And, well, this is a test, though. I'm looking to see if two things are equal to each other, right? And so what's the second argument? So the first one's T0. What's the second one? I want to see if it's, what's the thing of T1 equals 0? Let's maybe make this T1, right? So the question is, if T1 equals 0, so if T1 equals, and what should my second command be for this? Should I put the constant 0 in here? Register 0, so what's that? $0, and then $sign spell out 0. So why does this exist? Because this command only takes one constant, and we're getting ready to use it over here. So I can't put two constants in here, and therefore this one can't be a constant, so I'm going to have to create a register because we're going to use it all the freaking time. And in fact, $0 it's a register, and guess what it has in it? All zeros. Okay, now the question, what number do I put here as the number of lines down? Because we say it's L1, but we already know the compiler converts that to something that says how many, no, don't tell me the label, how many lines up or down from where I am now do I want this programmer to go? And so what's the answer? 4 instructions down. So what do I put here? Do I put 4? Do I put 16? Do I put something completely different than that? You don't put 4, and you don't put 16. Why? What's the, yep. Right, instruction's 32 bits. If it's a byte address, yes. So the question's going to be, so that's really the argument. But I'm telling you in this case, even though you tell me it's 4 instructions down, this one, this one, this one, this would be 4, 8, 12, 1, 2, 3. I need one more, right? 4 instructions down, 4 bytes, 8, 12, so it shouldn't be 16. I'm telling you that's not correct. Why not? What's the very beginning of this problem say? It sounds like extra stuff in there and you don't know why I did it. You load a branch command from instruction memory, and then I say this, as you begin to process it. Let's go to the laundromat. You hand the person, you've got somebody that helps people take clothes out of the car and bring them into the laundromat. So somebody comes in with a basket, they've gotten it out of the person's car, they bring it in, they hand it to the processor. They hand it to the person processing clothes. They do what with it? Well, but what are they? Yeah, so they're going to hand it to the processor, the person. What's that processor's job in a laundromat, would you suppose? In the analogy that we kept using, right? What's the first stage of washing your clothes? Put it in the washer, right? So they're going to put it in the washer. What do you want that employee doing that brought the basket in? Standing there watching the clothes go round and round? Exactly. Getting the next load of laundry, right? Going out and getting the next load of cars. So they're not worried about that instruction anymore. Do you remember I told you as soon as you load one instruction, the program counter immediately increments itself to the next instruction? It's already pointed right here. It's not even, couldn't care less about this anymore. Mission accomplished. It's not going to stand back and enjoy its work. You know, it's already got it loaded in. It's going to get the next instruction. So it's already calculated the address. It's just waiting for you to tell it go. And instead, what you're going to tell it is, I want you to go someplace else. So how many lines down is it now? Just 3. And how many bytes per each? He said 4, right? So that would be then what? 12. You could answer this as 12 bytes or 3 words or 3 instructions. Either one will be counted as correct, but it's not 4 and it's not 16. All right, makes sense? So just think about the laundromat. If you're the boss, once the kids brought in the basket of clothes, you're like, get the next, there's a customer waiting. Take their order. Don't take the order at McDonald's and turn around and watch them cook the burger. No, take the next order. It's exactly like that. That made sense? Okay, consider the following MIP snippet, implementing locking and synchronization. All right, so we have a move command, we have a load linked, and a store conditional branch if equal to 0. It's kind of a shortcut pseudo instruction. Move, which is also a pseudo instruction. And then 1, 2, 3, 4, 5, 6, 7 possible answers, which you can't see. But you can now. Okay, so which are the commands that we learned last week dealing with making sure we could monitor if somebody else was messing around with our memory location? In this block of code, which 2 is it? Which 2 instructions here look weird to you? New. Yeah, LL and SC. So how many, those of you who answered that, how many of you were absolutely positive and you knew that was the answer and were not guessing at all? And so the rest of you were doing it on gut instinct? That's correct. Trust your gut. Right? That's the correct answer. It's LL and SC. So what LL and SC did is you tell LL, look, I'm getting ready to run some code that's going to update the value of this location in memory. Will you please keep an eye on it and let me know if anybody messes with it while I'm gone? I'll be back in a little bit, and when I come back, I'm going to ask you to please store this in there, but not if anyone's touched it. Just let me know. Right? If anybody's messed with the food while I've been gone, do not serve it. So this one has nothing in between the 2. That's unusual. You would normally have lots of lines of code between the LL and SC, as few as possible, because the longer this block is, the more likely it is somebody's going to come and mess with it. So when you finally come back and you run store conditional is going to know whether anybody else has been dealing with this protected location, and if it has, it's going to not store. It's going to give you a result code that says, I didn't do it, and you're going to branch back up and try it again. So with that as the explanation, what is it that's being protected here? Is it T0, S4, S1, 0, S1, T1, or try? Which one do you think? Looking at the code. So it's going to be, you're going to have to tell load linked what it is you're protecting. And then when you come back with store conditional, you're going to ask him if anybody's messed with it. So what do they have in common? They have 0, S1 in common, right? Yeah. Right here. So you could guess 0, S1 and you'd be right. That's what's being protected. What's a little weird about this is you're basically saying take the value of T0 and store it in 0, S1. And when it tries to do it, it's going to overwrite what's in T0 with either a 1 or a 0. Well, it's going to set it to a 0 if it failed. So if what you were trying to put in there already was a 0, it gets a little complicated. And if what you had in T0 you wanted to keep, it also gets complicated because it's erased it. So you have to have a little more programming experience. This isn't enough to know how to really use these, is my point. They're just kind of introducing to this. Okay, so that's what we're trying to protect. Great. What feature of a computer's architecture required that we ever even came up with this crazy synchronization ability? What is it we changed about the way our computer worked last chapter that caused us to need to start worrying about synchronization? We never had it before.
2 processors can delete in one address at a time.
Yeah, back to that thing, right? Back to your that thing again. 2 processors, 2 cores, parallelism. more than one person that can mess with the same location at the same time. That's what caused us to have to do this. And it's now in everything because everything is parallel. All right. We good? So one of the most interesting homework solutions I've ever read anywhere, including in my classes but outside, was one I read yesterday from a student in China who was given not just a handful of problems in Chapter 2, but the class that this student takes, they gave them every single problem in the end of the chapter. They had to do all of them, 2.1 through 2.43 or whatever. I'm like, oh my God. So is this true? Does this happen? Do Chinese instructors do this regularly?
I studied abroad in Hong Kong, and yeah, that's pretty.
That was astounding to me. So the student wrote the solution for this whole chapter, and they get to these problems with CPI in them again, which we covered, remember? We covered a couple of homeworks ago. It was a couple of chapters ago, but here it is back again. And it's not really talked about in this chapter, is it? But I think they put it in the wrong chapter. So the student I read last night said, these problems don't really pertain to this chapter. I don't think it's a priority to learn these again here, and I'm not. Doing 40 of them, you're like, enough already. But for us, it makes sense to do it because it's still in the first half of the class and we're going to have it on the exam, so it's kind of a practice. All right, so in this problem, we found a way to reduce the number of arithmetic instructions by 25% while increasing the clock cycle time by only 10%. All right, so 25% reduction in instructions. What do we change in this table? And what do we change it to? Don't everybody answer at once. And what do we change it to? So you're saying change the number of arithmetic instructions from 500 million down to what? 375, 3/4. Okay, and then what are you going to do with the clock cycle time getting longer? Well, first of all, what is clock cycle time?
Number of cycles. No. The time that one cycle finishes.
Yeah, the time for one cycle to finish. Clock cycle time. The time on the clock for one cycle to happen. Do we have a field in this table for that?
Actually, we convert frequency.
So when they tell you a 4 gigahertz system is faster than a 3 gigahertz system, we believe them, right? When you're picking your Intel chip. So is that clock cycle time? So what does 4 gigahertz mean anyway? Yeah, which is how many? Do you know? 4 billion cycles a second. So 4 gigahertz is 4 billion cycles a second. So what is 100 megahertz? 100 million cycles a second. How much do each of those cycles take? Flip it. 1/100 millionth of a second. If you put 100 million of them together, and each one of them takes 1/100 millionth, you have 1 second at the end of 100 million of them. So if I'm increasing the clock cycle time by 10%, I'm taking 1/100 millionth times 1.1. and then flipping it back upside down to get my new megahertz value. So what I did in the table for you guys was I just gave you the blanks to fill in, and you can type into it if you want to do it in Word, or you can write into it if you want to do it that way. Everything else you can calculate kind of from those. So what you're after really is kind of maybe the CPU time, maybe the CPI. So if I'm asking you at the end of this, is this a blah, 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 where we go here? Is this a better choice? Should you take the bet? Should you do this? Is this a good design choice is actually the question. So you'll know, how are you going to decide if it's a good design choice? If the CPU time decreases. Is there another measure that you can use in this case? Is there anything else that would go up or down by itself that would tell you whether it's a good decision? Or is it just CPU time in this case? I think it's just CPU time because everything else is changing. So we don't have really Apple, but the duration of a second did not change from one to the next. So lower answer means less time. All right, a couple of others to go through here. A couple of other examples. One of them is you've got somebody that comes along and they tell you they're going to double the math performance. What does it mean to double the performance of that first row of instructions? So 500 million instructions. What are you going to change in that first row? You change one and I'll calculate the other for you. So which one are you going to change, cycles or CPI?
CPI.
So what's likely to have happened on a computer that would make it actually take half a cycle? I mean, half a cycle, don't you have to have like a whole cycle to do something? It's a cycle, right? I mean, what do your clothes look like after half a cycle? Like, that doesn't make sense, right? So what does it probably really means going on here if somebody tells you they only need half a cycle? Bingo. Parallelization. They're doing two at once. So what you'll find people will often do, instead of telling you it's half a CPI or a tenth of a CPI, they'll invert it and tell you how many I's per C instead of C's per I. They'll tell you 2 instructions per cycle or 4 instructions per cycle, but it's the same. 2 instructions per cycle doubles your performance. It's the same thing as 1/2 of a cycle each. So I would change CPI to 0.5 and calculate the rest through. So let me ask you, now how are you going to tell whether you're better off with this design than the one above? What metric are you going to use here to compare it to the previous example? We all know it's going to be better, right? Because it's going to take half the amount of time for arithmetic, and there was no penalty for the speed of the clock cycle. Megahertz stayed the same. So what are you going to show me as proof? How are you going to calculate the speed up? CPU time difference? A ratio, right? Is that the only way to do it? You can also use the CPI. Why can you also use the CPI? And one other really critical fact, the speed of your clock didn't change. So the cycle is the cycle is the cycle on both of them. It's exactly right, as long as I don't change the clock time on you. If the clock time stays the same, then cycles per instruction is exactly the same answer. You're going to get exactly the same. So you can probably find these answers on the internet because it's the same problem. But what you won't find are these tables, because I'm forcing you to kind of fill out a few fields on the table so you have a prayer of understanding how you did it, instead of just like jumping to the answer. Okay, this one claims to increase the performance tenfold. I have no idea how I got the little dots on there. Tenfold. So what are you going to change on arithmetic now? If you have a way of improving the performance of arithmetic instructions by tenfold. 0.1, or flip it upside down and say 10 instructions per cycle, and then just invert it back again. All right, good. Okay, down here for the last few, what is 5ED4 minus 07A4 when these values represent unsigned 16-bit hexadecimal numbers? The result should be written in hexadecimal. Right, so should we just try one real quick? 1 sneeze means yes, 2 sneezes mean no, so I'll take that as a yes. My dog does this too. Okay, what's 5ED4? 0, 1. What's E? In decimal, what is it?
13.
Is it 13 or 14? 14, right? Which is 8 plus 4 plus 2 plus 0. And then what's the next one? D? 1, 1, 0, 1, right? And then 4, 0, 1, 0, 0. And we're doing subtraction. And 07A4, 07A4, which is 1010, 0100. Remember how I told you when you do this long enough, useful stuff leaves your mind and it's replaced by stuff like this. I used to know some line from a Star Trek show probably, and now I know this instead. Okay, so let's try it out. 0 minus 0, 0, 0, 0, 0. That part was easy. 1 minus 0, 0. What are we going to do here? 0 minus 1. 0 minus 1, what do we do? What did you do with decimal? If you had 120, yeah, 124 minus 72. This part's easy. What did you do for the minus 7? You borrowed 1. What became of that value when you moved it over here? Did it stay as a 1? What did this 1 become when you moved it over and added it here? A 10. Agreed? Okay, so I'm going to borrow this 1. I'm going to bring it over here. What's it going to become over here? A 2. Seems weird, doesn't it? So 2 minus 1 is 1. 0 minus 0 is 0. 0. Do the same thing here. I bring a 2 over though, right? 2 minus 1 is a 1. And then I have 0 minus 1. I have the same problem. I'm going to get rid of this. What am I going to put here? Another 2. 1. And this is going to become a 0. I'll put a 2 here. That's a 1. 0. 1. 0. 1. 0. All right, things look okay. But what I forced you through was to understand exactly what's going to happen with carry, because you may have learned this for your whole life and never really understood exactly what was happening with carry. That's been my experience.
Why?
This will force you through it.
Yeah.
I screwed one of them up. Yeah, like that's a big shock, right? So yeah, so write the correct answer down, okay? You know, yeah. Which one did I mess up?
The fifth from the right.
1, 2, 3, 4. Well,
Yeah, that one right there.
well, how do you know I'm using the same numbering system as you? Yeah.
With the
Okay.
2 and 2.5
No,
number.
yeah, the 2.5 numbering system. All right, we're almost out of time, but I'm going to preview one of the other ones here. The second one I think has the same answer as the first one, if I remember correctly. The next one has 105 and 72, and we're going to subtract those. Does anybody know what 105 is? It's 64 plus 32, which is what? 96. And then how much do I have left to go? 9. So it's going to be 1001. All right, so that's 105. And then the other one is 72. 64 and 8, right?
Yeah.
Okay. Whoops. I think that's right. And now I'm going to subtract these. 1, 0, 0, 0, 0, 1, 0, 0. That one was easy. So let me ask you a little more complicated question. Let's say I'm adding these 2 numbers, and now I make it these 3 numbers, and now these 4 numbers. What is this one? 1. What is this one?
1.
What is this? 4 is the right answer. It's not 1 or 0. It's 4. 1 plus 1 plus 1 plus 1 is 4. How do you write 4 in binary? How do you write 4 in binary? Quit trying to guess the answer and just let's do it little by little. How do you write the number 4 in binary? It's 1, 0, 0. Correct? That's exactly what you're going to write down. You're going to write this bit is going to go here. The next one's going to go here. And the third one's going to go next to it. 1, 0, 0. So we can basically write it out this way. So you're going to end up carrying something into 2 positions. You ever done that before? No. It works exactly like you'd expect. It's a 3-digit wide number. It's going to take up 3 columns in your answer. So 1, 0, 0, huh? So the 0 is here. And then you're going to have another 0 here. And then the 1's going to be over here. So 0, 1, 0. This is a 0 here as well. Now I have 2 of these things over here. What's 1 plus 1? 1 plus 1?
0
1 plus 1? 2. How do you write 2 in binary?
1, 0.
1, 0. Don't freak yourself out on it. It's like grade school stuff, but we never teach really how to do carry and things like decimal. And so you show up to do binary and it makes it twice as hard as it should be. If you end up adding a bunch of numbers up and you come up with a number that's 5-digit wide, guess what? It's 5 digits wide. Each one of them is a positional numbering system. They have to take their right positions to the left of where you are. Make sense? Right? Does that surprise you guys a little bit? It's a little strange, right? You want to do another one?
Yeah.
Let's try one more. Get a little more. Get to where you like it. Okay. Let's see. We have 1010, 0110, 1010, 0111. All right. What's the first column?
1.
First column is a 1. And what's the second column add up to?
4.
4. Thank you. Almost everybody said it right. So this is a 4, correct? And how do I write 4 in binary?
1, 0, 0.
So I have room only for one of them here, though, right? The last digit, you said 100, right? The 10 get added up here in the correct positions. So now I have 1, 2, 3, 4, 5 digits. What do they add up to?
2.
2. How do you write 2 in binary?
1, 0.
1, 0. And I only have room for the 0 here, right? So where does the 1 go?
Here.
Up here. And now this adds up to 1, 2, 3, 4. How do I write 4 in binary?
1, 0, 0.
So I have a 0 here, and I have a 1, 0 up here, but there's nothing else to add to them, so I can just bring them right on down. You can do that. Yeah, I see some smiles. New stuff. The old guy has a couple of new tricks up his sleeves after all these years. Okay, have fun with this stuff. If you get stuck, text me. Short deadline on this. I'm not going to crucify anybody for not having it out, but I will need to release the solutions probably by next class. So if you need to take an extra day, take one. Don't take a bunch, because we're going to have to crank out the solutions for these so people have them to study. And when you get the solutions, you know, there's a chance I have errors in them because I had to go fast too. Just let me know, please, if you don't agree. Thank you. Yeah. If you don't have a calculator that can do hex and binary, borrow or invest in one would be my advice. I'll try to give you a table, but it'll help your state of mind if you know how to use one. It's exactly the same. It's exactly the same. Yep. Correct. Yes. Exactly. Yeah, but in hex, the trick is going to be, it's not obvious in your head how to spread it out. So if you end up with a total in one column of hex, it's like 3,628. You got to be able to do how many of those are 16 to the 1, 16 to the 2, 16 to the 3. It's much harder. Much harder. Decimal and binary we can do here. The rest of them, forget it. Yeah. Don't forget with your power supply, whoever loaned me their power supply. Was that you? Okay. Bye, guys.
On my lab, I was doing lab 5, and I tried to build it, and then there was an error saying the target not created.
Is it spaces, or wonder what's making it? Any ideas what making it do that? Have you hit up your TA about it?
No, I submitted yesterday, and I was wondering, can I resubmit it, or is it too late?
Yeah, you should be able to resubmit as many times as you want. If you just override on top of it again, you figure out what it is, just put a note in there that says